Now that we've obtained data from our hardware layer, put it through our input mapping layer, modified it or simulated it, and we have it in our corresponding asset data, it's now time to start looking at what we do with that information and how we actually manage our assets. So on the screen here, we can see that we have two areas, instruments and devices. We're going to go into our asset management instruments section at the moment. And in here, we should find asset managers for each of our instrument assets. So we have IL01, DPO2, all of the instruments that are required for this project. And in this particular project, they're all of the same type, which is a simple analog asset manager. So what we can see when we first see a function block for analog asset management is asset data, like we saw on the input mapping layer. This time we now see an alarm group, and we'll touch on alarms in a different section, like I've said before, but we will start seeing more about alarms now. And then we have an alarm management input as well. And if we hover over these, we'll see that all of these are in-out. So in-out for asset data, in-out for alarm group, and in-out for alarm management. And we'll touch on why in-out is better. I believe that we have sort of touched on this already, but in-out is better because you're bringing everything to a pointer. So I know you can't see that when you look at this right now, but all of this is pointed. So we're passing by reference, not actually copying the information. And from a scan point of view and a workload point of view on the PLC, it's far better. We're not creating new copies of information every time we enter a function block. You do need to be careful with that though. That does mean that any changes you're making to the actual data block, IL01. You're not changing it in here. So if you have any asynchronous processes, like in a different OB, that jumps in and has a look at this information, you are updating that information in real time. Let's go in and have a look at the Analog Asset Manager's internals. So on the interface here, we can see that we have the in-outs that we've just mentioned and the output for scaled value and alarm active. They are only there for indication purposes because the actual information is put into our asset data. So scaled value, for example, will end up in scaled value here, and alarm active will end up in alarms, and then one of these will be active, and we just get a general group overview that says an alarm is active. There's lots of stuff to do with alarms, which I'm not going to touch on too much. We'll go through this in depth a bit later. We can also see that we have some simulation feedback as well in our asset data to say, is simulation enabled and what's the value? This is not to be confused with the simulation that we've just done. This is for soft simulation, so simulation of this asset, but from a project point of view. So again, we'll come on to this a bit later when we go through the simulation HMI, but there are two types of simulation: raw simulation and scaled value simulation, and that's what this is touching on here. So let's have a look at the actual code before we have a look at the statics here. So this is made up of other functions and other what will be library objects, other standard bits of code. So we have an analog scale function, which is here. We have some alarm management, which if I just scroll down, we can see here, high alarm, high alarm. They're all comprised of the same analog alarm manager. And we have one on its own here for out of range alarm manager, which is just an alarm manager. So these ones are analog alarm managers, and this one is just an alarm manager. And effectively what this is doing is taking in our asset data, which we've just looked at on the interface here. So it takes in our asset data and then applies all of the logic that we require against that asset. So at this point, we've already been through our input mapping layer. We already have all of our raw values. They will be sat on IO input raw here. We've already taken that in from our hardware through our input mapping layer and or simulation. Remember that at this point of the project, it doesn't know if you're in simulation mode or not at the input mapping layer. That's the whole point of it being there. Anything that happens in simulation mode will happen in normal mode, or not in simulation mode. So we can see that being used here. So raw value input, asset data IO input raw gets passed into the analog scale. We have a asset data dot scaling, which if we have a look inside asset data scaling is a UDT analog scaling, and that's passing in things such as or updating the raw value, so that will end up in the raw value here. And then we have raw min, raw max, scaled min, scale max. All of that stuff will be interactable on the HMI, so an operator would type in what the raw min, what the raw max is, what the scaled min, scaled max is, and then we end up with our scaled value and a percentage range. It's always worth adding in the little things like a percent, just because sometimes it's really useful to have that sort of pre-calculated stuff available if you need it. So we can see that what we have coming out of here is scaled value, and that's being put onto our asset data scaled value. So we have scaled value in more than one place. We have it in our scaling UDT, but we also have it in the actual asset UDT as well. And that's just so you don't have to keep drilling down into different areas of your data. But if we did need to pass this analog scaling function out, all of the data for the analog scaling out to a secondary function, the scaled value is in there as well. And you might think, when do you need to do that? But if you are converting a required output position that's in percent back into the milliamp signal that you want your output card to output, that's a prime example of having all of the UDT analog scaling packaged up into a nice data set that you can then pass to a dedicated function at your output mapping layer, or before you get to your output mapping layer, to generate that correct milliamp signal based on what your scaling requirements are. So once we've done the analog scale, we are then looking at whether we're raising any analog alarms for being out of range and things like that. We will go through this stuff as we go through the next lesson of breaking asset requirements into functions and actually have a look at why things are set up this way. But as a general overview of the asset management layer, this is the sort of stuff that we're doing. Managing simulation, managing limits, managing all of our alarms, and the key thing is ensuring that the analog asset manager does everything that any analog asset would require. It's not just a case of, if we go back and have a look at the actual instrument management layer, it's not a case of saying, well, this is a level and this is a differential pressure, so we'll create a level asset manager and a level analog differential pressure asset manager. We are looking at the bare bone requirements of an analog instrument, and what is it that every single analog instrument requires? Well, they will all require scaling. They will all require some sort of alarm management for out of range, and it's very likely that you will want the staple and basic alarms of high alarm, high alarm, low alarm, and low alarm. If we then find that something like a level then requires an additional thing such as near blanking distance fault or something like that that you use all the time, you can then wrap this analog asset manager in an additional layer called level asset manager, or analog level asset manager, or ultrasonic asset manager, however you want to do it, and encompass all of the functionality of this analog asset manager within your new manager. You can do everything that the standard and basic analog asset manager does, and then build on that with your additional requirements and functionality. And doing things that way means that if you ever come back and update your analog asset manager, the new and higher level asset managers that make use of it will automatically be updated as well. And as we go through the course sort of further and we see more requirements that are needed to build our solution, we may find that we do need to update and upgrade some of our asset management, including creating new wrappable layers that make use of what we've already done. So in short, that's the sort of thing that we're looking at in the asset management layer. It's all about taking in the information that we've obtained from our input mapping layer, manipulating that, setting conditions on that. But most importantly, the thing to understand is that everything is contained within the asset data. So I know we've got alarm groups coming in and we've got alarm management coming in, but even then, the condition and state of those alarms are stored within ILO1 and the typed value here. And it's really important to understand that when you build your system, it might sometimes feel like you have information in more than one place, but from a containerized point of view, having everything that you need for that asset in one place that is a UDT and is able to be distributed across your entire project, across comm systems, across HMIs, across SCADAs, it makes a big difference to having to pick out information from different places. So we might manage our alarms on this alarm data here, but we can access the state of those alarms from an asset point of view on this data here. And again, as we go through interlocking and alarms, more and more of that will become easier to understand. So in our next lesson, we're going to go through this analog asset manager from a function point of view. We'll jump into things like the scale block and the alarm block and have a look at how our data works with those functions and why they're set up the way they are. Also touching on little things like, the interfaces of these sub-functions are done in a particular way that allows them to be used with other data groups, with other sort of UDTs or without any UDTs at all. So you have smaller building blocks for your asset managers, but they can be used in their own right as well to help build other asset managers or other control layers and things like that. So it's trying to keep that in mind. But we're getting into the basic building blocks of this system now. So hopefully you'll start to understand why things are done that way and see the benefits of why, when they're built that way, what benefits we get out of it. As always, if you have any questions, just drop them in the comments below or message me on LinkedIn, and I'm happy to go through this and update the lesson with anything that people are asking.